Okay, so today we're going to do rotations and tessellations. So remember, rotation just means you're turning, and tessellation is a pattern, kind of like the Texas that's on the door. So let's look at rotations. So a rotation is a transformation. We're going to see if we can get this to type, so we'll see what happens here. So a rotation is a transformation that turns a figure about a fixed point, called the center of rotation. And that is very hard to read. So let's change the font to something that's a little more readable. All right, there we go. So center of rotation, okay? Now rays drawn from the center of rotation to a point and its image form an angle called the angle of rotation. And I'm probably going to spell everything wrong over and over and over. So the angle of rotation, and again, I will change the font. I don't know why it keeps going back. There we go. Angle of rotation. All right. So let's move that word up. All right, there we go. Now, a rotation is also called a turn. And an object and its rotation are the same shape and size, but the figures may be turned in different directions. Okay, so now that is how we're going to do rotations. Okay, so now let's look at some properties. So some properties of rotations are, and some of these things are super important, so we're going to highlight them. So properties preserved under a rotation. The angle measures remain the same. Parallel lines remain parallel. Points stay on the same lines. Midpoint remains the same in each figure. And the lettering remains the same, so you can't change the order, okay? So a rotation turns a figure through an angle about a fixed point called the center. So these are just some properties. All right, so here we go. So when working in the coordinate plane, assume the center of rotation to be the origin unless told otherwise. Okay, so unless you're told otherwise. A positive angle of rotation of the figure is counterclockwise. So positive is counterclockwise. So if you think, okay, so, oops, let me see if I get this. So if you're in a grid, so let's see if this is going to let me write. All right, so let's just say we're in the coordinate plane. Counterclockwise means you're moving this direction. Okay, so this is considered counterclockwise, and that is a positive angle, so that's going to form a positive angle. That's why the coordinate plane is in quadrant 1, and then you go this way to get to 2, then you go down here to get 3, and over here to get 4. So it goes in a counterclockwise direction. That's what makes it positive. A clockwise, so you know the clock would go this way because that's how the numbers on a clock go. So you have 12, 3, 6, and 9. So it gets greater going that way. That will produce a negative angle. You'll get more into that later, but I have to make sure that I point it out. Okay. So when you're going to rotate, so remember when we did reflections, how if you reflected over the x-axis, it had a set rule, and if you reflected over the y-axis, it had a set rule. Well, the same thing applies when you rotate. So when you rotate 90 degrees, you're going to use the capital R with a little 90 there, so that means rotate 90 degrees. Your xy will become negative yx. So they change places, and the and the y will change signs. If you're rotating 180 degrees, so think about if you're rotating 90 degrees, so from here to here is 90 degrees. From here to here is another 90 degrees. That's why from here to here is 180 degrees, because you have your straight line. Now to go from here all the way to here is 270. And of course, if you go all the way around, you have done 360, otherwise known as doing donuts in the parking lot when it's icy out. All right, so now 180-degree rotation. This will give you the same order, so they're going to stay in the same order, but both of their signs will change. So this is also the same thing as the point reflection and an origin. So if you do a point reflection, it's the same thing as rotating 180 degrees. And this is all on your cheat sheet too that I gave you. And then if you rotate 270 degrees, they change again, just like they did up here with 90, but this time the X will change signs and the Y will stay the same. All right. So now here's your unit circle. This is considered the unit circle. Those of you going into pre-cal, calculus, things like that, this will become a whole lot more familiar later, but now you've at least heard of it. So please remember, quadrant 1, rotate counterclockwise to get quadrant 2, keep going counterclockwise to get quadrant 3, keep going counterclockwise to get quadrant 4. Okay? And that is how you do rotations. All right, tessellations, if you'll notice, I have all these little patterns and they're all the same pattern that just keeps repeating and they fit inside of each other. So this blue one fits inside of the pink one, fits inside of the turquoise, and so on. So these are called tessellations. A tessellation is a design or pattern in which a shape is used repeatedly being the key word here, to cover a plane so that there are no gaps, no overlaps, and no empty spaces. So everything fits together perfectly. Regular tessellations is what we're going to be focusing on, and it's a pattern made with only one type of regular polygon. Remember, regular means all their sides are the same, all their angles are the same. So this would be a tessellation of equilateral triangles because all of those are the same. This would be a little tessellation of irregular little monsters. All right, so this is how you check to find out if you can make, good Lord, what is all this? Okay, so this is how you're going to find out if a figure will tessellate. So I have a triangle, a square, and a hexagon, and I'm just going to test. You have to use this formula because it all depends on this interior angle right here, okay? So everything is going to depend on that interior angle. So now, if I go back over here, so we know that an equilateral triangle has 3 equal sides and has 3 equal angles, okay? Do you remember how there's 180 degrees in this triangle and there's 3 angles, so that means each one is 60. So what you're going to do here, at first it says the sum of the measures surrounding a point or vertex must be 360. I'll explain what this means in just a second, okay? Only regular polygons that have an interior angle, so the interior angle, that has a factor of 360. So what you're going to do is you're going to take 360, divide by that interior angle, and I get 6. Since it goes in evenly, then I know this, yes, it's going to tessellate. Plus I already knew that. It was the one on the other page. Okay, this is a square. So we know in a square all the angles are 90. So all you have to do is take your 360, divide by 90, and you get 4. So therefore, this will tessellate. Now I have a hexagon. Okay, hexagon, maybe you don't remember the measure of this angle, so we're going to go 6 minus 2, because we're going to use this formula up here, times 180 divided by 6. So I've got 4 times 180 divided by 6. So this is 720 divided by 6. So one interior angle is 120 degrees. So now you take your 360, divide by 120, and you get 3. So yes, a hexagon will tessellate. But what about these? Will these tessellate? Okay, so first of all, this is an octagon. So to do the octagon, you have to check. So we've got 8 minus 2 times 180 divided by 8. Do it all, and we get 135. Okay, so the interior angle is 135. So test 360 divided by 135, and you get 2.6. So since it does not go in evenly, no, this is not going to tessellate because you're going to have gaps or overlaps. And of course, these are not regular polygons. You have a rectangle and a trapezoid. They're not regular polygons, so they're not going to tessellate. I can use them with other figures to tessellate and have an irregular, but to form a regular tessellation, you have to have a regular polygon and it has to be a multiple of 360. So now, let's see, I told you that we would go back to this concept here. All right, so this is where this comes in. What that means is they were talking about all their vertexes meeting here. So this is a semi-regular tessellation because I have a combination of two regular polygons. I have a octagon and I have squares. So in an octagon, remember we just found out that this angle right here is 135. So that means this angle right here is also 135. Since this is a square, this angle is 90. So what they said is you have to see where they all meet, so all their vertices meet right here, and it makes a circle, because 135 plus 135 plus 90 equals 360 degrees, just like in a circle. So that's all that this one bullet right here was saying, the sum of the measures surrounding a point. In other words, they all meet right here. So those three angles would have to add up to 360. In irregular tessellation, this is where other figures can make tessellations, and they're going to be irregular, of course. The figures used are irregular polygons, and they may even be different shapes and sizes. So it's an irregular tessellation. Again, the Texas tessellation that's on the door, that would be an irregular tessellation. The very first image that I used when I introduced tessellations, all those little bright shapes, that would be an irregular tessellation. So tomorrow we'll do lots of practice with this, and I'll see you guys next time.